Welcome everyone, my name is Zachary Abraham.
I'm Amanda Kwan.
I'm Talia Solomon.
I'm Michael Shea.
And I'm Karina Yang, and our project is the control of an affordable hand and wrist prosthesis.
So for today's presentation, we're going to start off by talking about our objective, and then we're going to go into the background of our project and the hand that we designed. We're then going to talk about how we planned out our project design and why we chose to go down the path that we did. We're going to go into the technical procedure of the project, and then we're going to finish off with the conclusion and some future applications. So the objective, as you can see here, was to design an affordable and customizable hand and a control mechanism to control the hand that would be functional and easy for the user to use. The hand would be for amputees with lost functionality below the elbow on their forearm.
There are many issues with modern prostheses. One major issue is that amputees stop using their prosthesis because it's too long, too short, or it weighs too much. This can make movement uncomfortable and unnatural for the amputee. This creates a problem because amputees can develop overuse injuries in their other arm if they don't use a prosthesis. Another major issue is cost. Most prostheses start at around $10,000, and this price can increase very quickly with additional surgery. There are also a lot of different methods for controlling prostheses. One method is myoelectric sensors, which are placed on top of the residual limb. However, these sensors struggle to accurately record the data necessary to control a prosthesis. These sensors can also be implanted inside the residual limb. There are other sensors that can be implanted into your brain. However, the surgical procedures for these control mechanisms are very costly and have long recovery time periods.
Our project utilizes 3D printing technology, which involves additive manufacturing or building objects layer by layer. This technology is becoming increasingly accessible since personal printers and public printers are becoming more available. This technology is also fairly low cost since the most available and popular 3D printing filaments, ABS and PLA, cost an average of $29 per kilogram, and people using public printers can pay by the centimeter. Furthermore, the designs and the technology are fairly customizable since the technology is based upon computer-aided design, which can be altered from amputee to amputee based on the sizes of their residual limbs.
For the design of our hand, we decided to use the Infinity Hand, which was developed here at Rutgers University by our mentor senior design project team. As for why we chose it, essentially accessibility. We had a model that we were able to work with that allowed us to develop the software while the parts of our hand were being printed. This allowed us to focus more on the control aspect of the prosthetic hand rather than the hardware. As for the control methods, we had a couple of different options, one of which was the brain-computer interface, which takes the data it reads from the sensors on the amputee's head that read the brain waves, and then that data is translated into motions on the prosthetic hand. But because of one, the underdeveloped nature of the technology, as well as the fact that this was extremely expensive, we decided that this was not affordable enough for our project. We also considered putting electromyography sensors on the amputee's hand and then having those sensors read the muscle activity and then translating that data into actions on the prosthetic hand. But then because there wouldn't be enough sensors for the readings to be very accurate, as well as the fact that it would look extremely messy on the amputee's arm, we decided that this wasn't a feasible option either. And that's when we found Maya, which is an armband developed by Ophthalmic Labs, and it has EMG sensors on the armband. And those sensors read the muscle activity, and then we were able to translate that data into motions on the prosthetic hand. We also decided that because the Myo is only $200, it fit our qualification for being affordable.
For the hardware, the hand consists of 5 fingers surrounding the palm. The palm has 5 servo motors in it. Servo motors, unlike regular motors, can turn a very specific number of degrees rather than continuous motion. By this system, we were able to thread fishing line from one tip of the servo motor through the fingers to the tops of the fingers. That way, when the servo motors turn specific degrees, the fingers actually move those same amount of degrees. Additionally, the wrist, rather than fishing line, is operated by a gear system because the hand itself actually weighs a considerable amount, so the gear system allows for more support because fishing line wouldn't have been strong enough. The one major difference that we added to the Infinity Hand design was a palm cap. The palm cap, as you can see, provides one protection for the servos rather than the servos being exposed. Now they are nicely secure by means of the palm cap, and additionally the aesthetic improvement to the hand. Rather than seeing motors turn constantly, it looks more like a regular hand and more pleasing to the eye. Finally, the software aspect. We realized that the Mayo operates on one software and the Arduino microcontroller operates on another software. We needed to figure out a way to integrate these two softwares, and what we found was MyArduino. MyArduino was developed on the Mayo beta market, and what it does is exactly what we wanted it to. It takes the output information from the Mayo, which is over Bluetooth, converts it into serial communication, and by that method it can now send it through the Arduino to the servos, which actually control the fingers. Finally, the 5 poses of the Mayo are preset. The Mayo can actually recognize 5 distinct hand motions, as you can see, based on the user's hand, and as a result, it can actually translate into 5 specific motions.
So to extend the functionality of our hand, we decided to add a variable grip on the fist. This meant that when the hand went into a fist, the fingers would be able to adjust the degree to which they closed. So to do this, we saw that all 5 poses were already used by other functions. So we went to use the inertial measurement unit, or IMU, that was already installed on the Mayo armpit. So the IMU was able to return angles in 3 axes: roll, pitch, and yaw. And with the roll angle, we were able to detect a rotation of the arm along the axis of the user's forearm. With this, as the user rotated, the fingers would either close or release in degree. We made sure that the user's rotation degrees were in a comfortable range so that the amputee would not have to overextend their arm in either direction. So here behind me you can see a graph of the roll angles that were returned for one certain example. So here you can see that the user starts at a near 0 degree, so he starts with his arm straight out, and then rotates to 1 maximum, and then rotates to the minimum, and then repeats the action. And at the end, when you see the line flatten out, the user stopped moving his hand.
As for the results of our study, the final weight of the prosthetic hand combined with the prosthetic wrist was 496 grams, and the approximate final cost was $635. This is much cheaper than the other prostheses that are on the market today, especially when you compare the types of technology that we're using. As for the control, we were able to accurately use the 5 preset poses as well as have variable grip strength.
It's important that we listen to amputees' desires while designing a prosthesis. In one study, it was found that amputees liked myoelectric sensors more than any other kind of sensor because they were inexpensive, user-friendly, and because they were non-invasive. This means that amputees were willing to compromise on functionality in order to get easier usable product that was easier to use and that was more affordable. In another study, it was that compared an adaptive prosthesis and a prosthesis that has variable grip in the whole hand and in each individual finger to a non-adaptive prosthesis, which simply opens and closes without any variability in the degree of closure of the hand. That amputees liked the non-adaptive prosthesis much more because it weighed a lot less, so it was more comfortable for them. Our prosthesis weighs less than the non-adaptive prosthesis used in this experiment. So it is closer to the weight of a human hand, which is about 400 grams without the wrist. Also, our prosthesis has some of the functions of an adaptive prosthesis, and the rest can be added in the future.
In addition to being used as a prosthetic hand and wrist for amputees, our device could also be implemented in industry to help workers with simple tasks such as pouring chemicals or operating machinery. This would reduce the amount of hazards that they experienced from day to day. This would increase company stability by reducing costs for liability, job rearrangements, and subcontractors, which all result from worker injuries. In addition, our device could be used in healthcare. Locally, this could reduce tremors in surgeons' arms that are due to fatigue and age, since the Mayo reads macro movements and muscle activity. The hand could also be included in a kit that could be deployed in remote locations or emergency situations in disaster medical aid centers. This kit would be able to contact on-call volunteer surgeons who could deliver time-sensitive medical assistance. Both of these applications would be very feasible since our device is portable and affordable.
So now before we close off, we'd like to show you a brief demo of what our hand can do. So,
So over here you can see the 5 fingers. The strings are threaded through the finger over here, and as the user rolls his arm from one degree to the other, the grip of the hand actually varies as such. The wrist mechanism is located in the bottom over here. It's controlled by a gear which is inside, and the servo motors are these, you can see they're kind of colorful. They're each connect to the solderable breadboard, which we wired up ourselves, and then connect it to the Arduino.
Alright, so right now the hand is at rest, and when I open my hand, this should, once this syncs up.
There. Oh.
So the software that we're using is already developed by Atomic Labs. It's called Myo Connect, and that's one of the connections that Myo Arduino uses to talk to Arduino. When you open up your hand, the hand opens up, and when you close your hand, the hand goes to a fist, and it changes its degree of closure, as you can see. So that allows the user to grip onto various different sizes of objects with this closure. And you can see it again here. And then we have a double tap functionality which shows a demo of each finger or motor moving. The demo is not as powerful, so the fingers may not be able to move as smoothly as it is.
Additionally, for the wrist action, although the gear system is relatively strong, the hand itself weighs a considerable amount. So as a result, the actual motor can only turn the wrist so much. Theoretically, if we had a larger span of time and a little bit of a larger budget, we could actually buy stronger motors which could support the wrist much more effectively.
So now to close off, our team would like to thank everyone who has helped us along the way. We have our wonderful project mentors, Dr. Con Lee, Dr. William Corelius, Julian Shu, and Mary Pat Ryder. We also have the Infinity Hand team who we thank for providing us with the design of this hand. We also would like to thank our resident teaching assistant, Kelly Rufinak, for all her help in the planning and the project. We'd also like to thank Dr. Eileen Rosen, the director of this year's Governor's School of Engineering and Technology. And we would also like to thank Dean Jean-Patrick Enchwan, the associate director for this year's New Jersey Governor's School of Technology. We'd also like to thank Rutgers, the State University of New Jersey, the Rutgers School of Engineering, as well as the State of New Jersey. And also, there are the gracious sponsors of this year's Governor's School that we'd also like to thank. Thank you for your time. We will now take questions. Yes.
How many total hours you spend on this device?
I'm sorry?
How many hours totally?
Oh, how many hours? More than we'd like to admit.
I think the schedule allots approximately 7 hours a day usually per week, not including weekends. So
sometimes more.
if you add that up.
7 hours a day.
Yes.
How hard was the hand to actually assemble? I know it was like an existing design. Was it difficult or was it like putting together Legos?
Karina, would you like to take that?
Most of the time was printing, so we printed for a considerable amount of time. And then a lot of it was fine-tuning with the wires and the rubber bands, because the rubber bands have variable amounts of elasticity, so we had to kind of play around with that. And we also had to design a palm cap for it, which took some time because there were 3 iterations of that, and then they all had to be printed. But the assembly is pretty stable right now, but it could have improvements.
How do actual amputee use it? So right now you guys are able-bodied and you were able to do the demo using one of your arms. So let's say there was a double amputee. How would you handle that situation?
Yes, that's a good question. So the amputee that this is designed for would have they would lose function below this area, so the Myo armband would still work above that part on the residual limb. So this hand could theoretically be attached to here, and you could use the muscle signals here to control the arm and hand. Yes.
How did you divide up the work among yourselves?
So we actually spent a considerable amount of time trying to figure out each person's unique skill set, and what we did was we kind of realized that Karina is very skilled in 3D printing. Michael and I, we know software very well, and Amanda and Talia, they're incredible researchers. So sort of, we really realized these unique skill sets, and we kind of, I think, made a pretty nice team.
Yeah.
How many degrees of movement can you control with your algorithm? Like, I know you use maybe rotation and yaw and
Yeah.
probably have 3 degrees now.
Yeah, so that's a great question. So we have roll, pitch, and yaw. So it's 3 degrees. You can either go roll or these other axes, right? So right now we only control this one axis because when you move in other axes, your arm inevitably changes the degree angles in other axes. So theoretically, if we wanted to control like a wrist motion or wrist degree with this axis, you could do that because we can get the values back. Right now we don't have to implement it because as you move this way, you're inevitably going to move a little bit this way and you're going to change the hand grip. So you have to find a way of differentiating between the 3.
So you can link one movement to one, I'd say you can open it up and maybe turn, but how about individual fingers? Is that
So that's a very interesting question. That has to do with the Mayo itself. As of right now, the Mayo is still currently being developed. You can go online and download the standard development kit and work on it yourself. But there are really only 5 specific positions because since it's reading the signals from the forearm muscles, it's not so easy to differentiate between this finger and this finger. So individual fingers is still being worked on, but things such as a fist or double tapping or wrist, that action is much more significant when it comes to the forearm muscles. So hopefully in the future, these functions will be developed and can be implemented.
We did find in the feedback from the gyro and the accelerometer sensors that when the fingers move, there are spikes in the data, so that could be used to develop additional function with each individual finger.
So I mean, it's possible to control each individual finger.
Yeah.
It's finding a way to process the data that you use.
Last question.
Last question.
In your demonstration model here, you have the computer connected to the Arduino and then into the fan. But in production, where would the Arduino component and where would the power supply come from?
Alright, so in future developments, we could use a smaller chip that would directly connect onto the solderable board, and that could be implemented into the hand.
Inside the palm?
Yeah, inside the palm. And then we also have a wireless communication with a laptop, let's say with an XV serial communication. That would allow, that would take out the need for a wire connection to the hand.
And the power supply?
The power supply we can add.
Yeah, a regular transistor would allow a separate power supply be implemented directly to the servo motors, and they only operate on 5 volts, so it would be a very small battery would be perfectly enough.